I'm Ross Stein. I'm president of the Tectonophysics section, and I'm pleased to convene this session on the giants of tectonophysics. And our first speaker in this session is Naomi Oreskes from Harvard University. And let me welcome her to the stage.
Okay, this is a little blinding. Thank you very much.
This is the mouse for you.
Okay, so
You can use it up there if you prefer.
I do.
This is the Mac mouse, so you're on
Okay.
a PC, so you're here. Does
Okay.
that look good?
So just click it.
You can click it or you can use
Oh, this is easier.
arrow.
Okay. Actually, I'm on, no, it's not. I was about to say, why am I
Oh,
on
I'm-
PC?
my-
Okay,
my
technical
error.
difficulties.
My error.
Good, I'll use this as an excuse to say, I planned a really beautiful 20-minute talk, thinking as an invited speaker I had 20 minutes. This morning I reduced it to 15, so hopefully it'll all go well. All right, so, it's still not moving. Okay, or is it this one? Oh, here we go. Okay, got it. So there's an old joke that many of you may have heard, that there's no such thing as tainted money, except taint enough. Now, as scientists, we have a tendency to think that because science is good, all money that supports science is good, and not to inquire too deeply as to how the needs, the goals, or the purposes of our funders affects our research choices and sometimes our research outcomes. But scientific studies of the matter have shown that research is influenced by the interest of sponsors, sometimes overtly, as in tobacco, but more often in ways that can be difficult to discern. So a few years ago, longer than I like to say, I set out to explore the issue in a domain where funding effects might or might not be present, or might perhaps be present but be more subtle. And that domain was American oceanography in the 20th century. As many of you know, in the 1930s, there were only two oceanographic institutions to speak of in the United States, the Woods Hole Oceanographic and the Scripps Institution of Oceanography. Both were small and poorly funded. Woods Hole had no year-round staff and no regular external funding. Scripps had a scientific staff of 11 with funds from the University of California for salaries, but nothing for research. And neither was truly oceanographic. Neither institution had facilities for deep-sea research. The focus was coastal and mostly biological. In 1940, Scripps launched its first expedition to the Gulf of California with a hard-won grant of $10,000 from the Geological Society of America. It was led by a young Roger Revelle. But money was so tight that the institution's director, Harold Sverdrup, shown here looking pretty worried, implored Revelle not to stay away even one day longer, for, quote, "we shall find ourselves in a deep pit when you return." But things began to change in the late 1930s when the U.S. Navy began to take an interest in oceanographic research for its military relevance. By the end of World War II, oceanography was a very different science, driven largely by military priorities, and mostly linked to questions in physical rather than biological or chemical oceanography. This is a memo produced by Richard Fleming at the end of the war, and you can see he identifies 9 areas of research that the Navy is interested in funding. 8 of them are in physical oceanography, and all of biology and chemistry is reduced to being of interest only because of fouling and corrosion of ships. So was Navy support good or bad? Well, it was clearly good for Richard Fleming and Roger Revelle, and others like them who built their careers on military funding and access to Navy ships. And it was good for Woods Hole and Scripps as institutions, which grew and prospered. And it was crucial to the development of plate tectonics. The military, particularly the U.S. Navy, funded the crucial work that led to radically improved knowledge of the ocean basins, and with that to seafloor spreading and understanding the mechanism of plate motion. At least, this is the standard story that has been told for a long time, that military support led to plate tectonics. But did it? It's certainly true that abundant data were collected on Navy ships under Navy auspices. But my argument today is that, in fact, key pieces of plate tectonic theory were already in place in the 1930s. But the conversation stopped because of World War II, and then was impeded after the war by military secrecy. And as I'll show you today, this is not just my personal interpretation, but the views of key scientists at the time, including Roger Revelle and Harry Hess. So if we look in the 1920s, we see there was a robust international conversation taking place at the intersection of oceanography and geophysics. In particular, in the 1920s, the Dutch geophysicist Felix Venning and his colleagues had gained international attention for pioneering work in the Dutch East Indies, which showed the physical coincidence between deep ocean trenches, earthquakes, and negative gravity anomalies. And several people linked these findings to the question of continental drift, suggesting that the observed pattern could be explained if two crustal slabs were pressed together and one or both down-warped into the trench. The down-warp would be the trench, the pressure associated would generate earthquakes, and the melting would generate volcanism. And some even argued that this large-scale pattern could be linked to mantle convection. This received experimental support from Venning colleague Philip Kuenen, who in a series of experiments suggested that, depending on the viscosity of mantle materials and the rates of compression, crustal folding could include low-angle thrusting of one slab beneath the other. And he called this downfold a tectogene. This work came to the attention of Princeton professor Richard Field, who was the advisor to a young Harry Hess. Field organized a pair of expeditions to the West Indies, to the Caribbean, and recruited Hess and Maurice Ewing to do this work. Hess and Ewing presented the results of these studies at a pair of conferences in 1937-38. The papers at the 1938 conference included this one by N.H. Heck, which showed the concentration of earthquakes in the Atlantic along the mid-Atlantic ridge. And this one by Hess, which attempted to synthesize the East and West Indian data. Hess argued that tectogenes were regions where the crust was compressed and a portion pushed down into the mantle. He did not think this was a peculiar feature of the Indies, but rather a global one. In 1933, he had written in a letter to Venning Mainz, "It is significant that only one negative strip was found in the East Indies, and that this strip was continuous for the length surveyed, 5,000 miles. It implies that deformation of the Earth's crust is taking place in a single and continuous narrow belt." Venning Mainz agreed, suggesting that this might well be evidence of, quote, "great lateral compression of the crustal material, and I cannot see another reasonable explanation than by admitting convection currents in the substratum below the crust." And Kuenen also agreed, quote, "admitting that the substratum below the Atlantic Ocean is covered by a rigid crust, the descending convection current must exert a viscous drag on the crust and be related to earthquakes that are occurring here." In 1938, UCLA professor David Griggs developed a physical model that could explain how this could work. And he used rotating drums to model the effect of subduction in a viscous mantle and showed that, indeed, an overlying rigid crust would be displaced horizontally and would cause thickening along the modeled continental margin. Griggs also estimated what the rate of crustal motion would be, and he estimated at 1 to 10 centimeters per year. So we see here that key pieces of plate tectonic theory were already in place in 1938. The notion of a rigid crustal slab, the idea of dominant horizontal motion linked to mantle convection, the linkage of orogeny, earthquakes, and volcanism to crustal motion, and even what we would now consider to be an accurate rate of crustal motion. Taking all this into account, Hess concluded, when the significance of these geophysical data and the structures they indicate becomes appreciated, a radical change in some of our ideas on mechanics and processes of mountain building becomes necessary. So what happened? Well, the short answer is World War II. Hess joined the Navy. Ewing turned his attention to Navy projects, particularly sonar. Venning Mainz joined the Dutch underground, and Griggs, after the war, went to work for the RAND Corporation. Still, we might have expected some or all of these scientists to have picked up the threads after the war, particularly Hess, for whom this had become his principal interest in the late 30s. But they didn't, so why not? So I'm going to argue that the short answer is secrecy. That after the war, the US scientists could no longer publish on these questions because of data classification of the key oceanographic information. Moreover, they couldn't even discuss them except with colleagues who also had security clearance. Nearly all the crucial data, particularly the bathymetric data, were classified. And throughout the 50s, Hess and others tried to get these data declassified. Indeed, Hess first raised the issue in a report on war work in 1944, even before the war was over. In a report to the AGU, he explained, quote, "much of this work is secret or confidential and cannot be elaborated on during the war." But he assumed that this would change when the war ended, but it didn't. So throughout the 50s, he tried to get the Navy to declassify these data. In one long memo entitled Classification of Factual Material of the Oceans, he argued that, quote, helping science required not just money, it also required broad dissemination of information, particularly what he called first-order information. By this, he meant basic factual data such as, quote, water depth, temperature gradient, magnetic field, gravity data, each coupled with a geographic position. These are the small building blocks on which scientific research depends and which ultimately may result in important theoretical conclusions. When basic data of these kinds were classified, it presented, quote, some very difficult and not fully recognized problems. If the prevailing policies of classifying basic data were not revised, he argued, it could well be quite disastrous by greatly retarding the development of several sciences and by limiting to a very few people the scientific know-how in dealing with a number of problems. Navy officers had argued that those who had a need to know had sufficient access, but Hess disagreed. Quote, those who need to know are an infinitely small number of our scientific population. The advances which could be made if the thousands of scientists freely had this information are all squelched. Inasmuch as great discoveries are very rare, we are in effect making almost absolutely sure that they won't be made by the simple procedure of limiting factual information to a very small number of men. Statistically, we have a foolproof means of impeding scientific discovery. Roger Revelle agreed. As part of the Department of Defense Joint Chiefs of Staff Research and Development Board, he wrote, it is the consensus of the panel that active scientific research is seriously hampered at the present time by placing new oceanic soundings under restricted or higher classification. Oceanography, argued, would be best developed, quote, if a wide interest in the topography of the seafloor can be stimulated among competent geologists and geophysicists. Such interest will largely depend upon ability to publish in the open scientific literature. Unless there can be a competition among scientists to solve the difficult problems involved, it may take 20 years to do what otherwise might have been done in 5. And Joe Wurzel at Lamont also agreed, on the whole, we consider that our entire program of topographic investigations has been seriously hindered, and most students who could have been interested in this work have bypassed it for other things due to the classification and associated ills of this work. And finally, even Maurice Ewing, who almost never complained to his military patrons, complained to ONR. I am sure that you will find all members of our group willing to delay publication of information as long as such delay is in the interest of national security, but the lifeblood of our laboratory is the right to publish, and it is my obligation as director to see that a suitable proportion of our work is on subjects where publication is possible. Finally, at Woods Hole, Henry Stommel called it the Navy's Iron Curtain. So to conclude, how do we know this mattered? We can see that the scientists involved thought it mattered, but can we judge in hindsight? I think the answer is yes. It's well known that in 1961-62, Hess offered his theory of seafloor spreading. What's less well known is that he did so in response to work in paleomagnetism by British colleagues, which prompted him to dust off his ideas from the 30s, and that the picture he presented in the 60s was essentially unchanged from what he had offered in 1938. So I don't have time to go into this in detail, but the key thing, if you look at his 1938 picture, we would say in hindsight the key thing that wasn't right is that the downgoing slab is horizontal, but if you look at the picture, the lower one on the right and left from 1962, the downgoing slab is still horizontal. So to conclude, given that more than 20 years had passed since 1938, given that the picture of crustal mobility given by plate tectonics in 68 was nearly the same as the one that Hess and Griggs had in 38, and given that the impetus for re-examining the question of continental drift came from largely outside the United States, the historical evidence supports the conclusion that secrecy did, in fact, impede scientific work. Or as Roger Revelle would have had it, it did indeed, quote, take 25 years to do what otherwise might have been done in 5. Thank you very much.
Are there questions for Naomi?
We'll have the next
Yes.
speaker come up.
Oh, and could I have the next speaker come up, which is Dawn, so we'll get her
I have
ready.
a question for Naomi.
Okay.
As you know, Hess was anti-drift. He was anti-drift until he reviewed what Rosie and Rosewarne had done in '59. Then he writes a letter to Benny Minez and says, basically, I've always been anti-drift, but now I've changed your mind because of the paleomagnetic data. I think you should do the same too. And when you talked about Benny Minez before, yeah, he did look at mobility, but that was only polar wandering. He was also anti-continental drift. And it was in part because of his work on the seafloor that he changed his mind.
Right,
Because
well,
people like Umbro before that were drifters.
yeah, well, we don't have time to discuss, oh, sorry, okay.
What was the important data from the seafloor that led, in fact, to plate tectonics and confirmation of seafloor spreading? It was magnetism. And the magnetic data did not start until Scripps towed that behind a ship in, 54 or something like that. So there wasn't a delay as far as the magnetic data goes, and that was a crucial data for establishing seafloor spreading from the seafloor.
Okay, well, we'll obviously have to discuss this offline because it's time for the next speaker, but thanks for that comment.
Thank you, Naomi. Our next speaker is Dawn Wright from Esri, and she'll be talking to us about Marie Tharp.
Thank you very much, Ross.
Glad to have you.
Thanks. So we're using this keyboard?
Yeah, and this guy.
Okay,
yes.
great. So it's a real honor for me to be in this session and to present this tribute to Marie Tharp in collaboration with my colleague Hallie Felt, who wrote what many of us consider to be the definitive biography of Marie Tharp. Marie was a woman who was very unusual for her time, with background and training in the 1940s in geology coupled with mathematics, in addition to music and art. And she also had the conviction of the courage of her conviction and her intellectual prowess to posit one of the most fundamental proofs of continental drift, which is the Rift Valley in the Mid-Atlantic Ridge caused by a faulting of an active seafloor spreading center. So I want to take some time to go through the history of Marie Tharp's process and her life in the short 15 minutes that we have. This is the 1977 World Ocean Panorama that many of us still consider to be our favorite map of the ocean floor. You see this around many oceanographic institutions across our country. I have a personal copy that is in my bedroom that is already faded. It's really a most beautiful map, partly because it was done in collaboration with an artist, Heinrich Beran, an Austrian painter. And so it's this combination of geological insight along with the available data, as well as the cartographic beauty. So many of us consider Marie Tharp to be the inventor of a field that is actually called marine cartography. And I work at a mapping company, the Environmental Systems Research Institute, so this is core to our mission. Now, one of the nice things about Marie in her background is that she was influenced by her father, who was a surveyor with the U.S. Soil Survey. And in an early age, you can see that Marie, little Marie here in the 1920s, was taken into the field by her father. She also had a very good relationship with her mother. It was a wonderful 3-person family unit. And there was never any question as to whether Marie would go to college, even in the 1930s. As you can see here, she's again in the field with her father. She became a geologist, but not until college. Her background included degrees in geology, but not until she had finished work with music and art. She was also a petroleum geologist with Stan Oil in the 1940s. Then she went back to get a second degree in mathematics. This is one of my favorite pictures of Marie in the 1940s. She's walking along in New York. At that time, she had been hired by what was then the Lamont Geological Observatory. She was hired by Doc Ewing, Maurice Ewing, initially as a general drafter, but she was promoted and became a research assistant, famously with Bruce Heezen. This is an early picture of Bruce from the 1940s, looking at the output of an early echo sounding system. She and Bruce went on to create, as we know, many of these so-called panoramas of the world ocean floor based on echo-sounding data, in addition to paleomagnetism, and also what was informed at the time with scientific drill cores. This is a very interesting picture because it shows Marie with varying forms of scientific data and maps that were used to communicate to other scientists, but also to the public, particularly through the New York Times and through the National Geographic magazine, what seafloor mapping entailed, so that you can see there, and I have a pointer that I hope will work, you can see that there is her, okay, we can also use that, great. So there's the famous map that she's working on. There are the single channel profiles from the seafloor. There are the profiles that she developed, and then also this beautiful handmade plate tectonic globe. So these are varying forms of science communication at that early time. Marie Tharp's process was very important, of course, to her success, not only in making beautiful maps with Bruce Heesen, but in actually discovering the Rift Valley of the Mid-Atlantic Ridge. She started off with ship tracks of available cruises at the time. Then she proceeded to work with the bathymetric profiles along those ship tracks. And very unusually, she ramped up the vertical exaggeration of those profiles to as big as 40-to-1 vertical exaggeration. And this allowed her to discover and to discern features in those profiles, such as this Rift Valley in the Mid-Atlantic Ridge. She would then draw artistically what the seafloor looked like along those profiles. And then finally, as you can see, those profiles have gaps in them. So she used her own geologic insight, her hypothesizing, a fair bit of extrapolation and interpolation to fill in the gaps, to give a picture of what the seafloor looked like in full, a synoptic picture of the seafloor. So that final panel, if we blow it up, that is her artistic rendition of filling in the gaps artistically between those profiles. This was not done haphazardly. Again, this was done through her own geologic insight and hypothesizing in collaboration with Bruce Heesen. The final very important confirmation of her discovery of the Rift Valley was this overlay of earthquake epicenters. And just like a modern-day GIS, this overlay confirmed that the earthquake epicenters lay right on the axis of the Mid-Atlantic Ridge, confirming that this was an active feature and, of course, part of the process of seafloor spreading. This timeline of discovery, I think, is very instructive because it shows not only the sequence of Marie Tharp's discoveries along with Bruce Heesen, but it also shows that there's a gap in her discovery and in the publications or the announcements of that discovery, and in her own ability to publish. She was actually not allowed to be a co-author on a publication until well into her career. She was not able to go to sea as a seagoing scientist until around 1968. But in 1952 came that discovery of the Mid-Atlantic Rift Valley. The announcement of the Rift Valley, including in the New York Times, occurred in 1957. In 1959, she was finally allowed to co-author on a Geological Society of America special paper. The North Atlantic Physiographic Diagram was published in that long paper, The Floors of the Ocean, the North Atlantic. In 1961, the South Atlantic Physiographic Diagram was published, coinciding with what Naomi has just mentioned in terms of Harry Hess's landmark History of the Ocean Basins. 1964, the Indian Ocean was covered in Heesen and Tharp's efforts in that physiographic diagram that was published, and this coincided with Bullard et al.'s fit of the continents around the world. We're going to hear later on in this session about J. Tuzo Wilson's defining of transform faults as a third type of plate tectonic boundary in a landmark publication in 1965. In 1967, Heesen and Tharp released the Indian Ocean Panorama as published in the National Geographic magazine, and this coincided with Jason Morgan's treatment of spherical geometry in terms of the plate tectonic boundaries, and we'll hear more about that in this session as well. These panoramas in the National Geographic magazine really opened up the eyes of the world to the fact that there was varying topography and activity on the seafloor. So this Indian Ocean panorama is, I think, one of the most beautiful. And if you go to Stanford University's Rumsey Map Center and you see this on a 20 by 40 foot hyper screen, it really comes to life. There's also the Atlantic Ocean panorama, which is a favorite of many because of the clarity that you can see, not only the mid-ocean ridge, but the transform faulting along the ridge crest. This was in the June 1968 issue of the National Geographic. And then, of course, the 1977 World Ocean Floor panorama that is so beloved. I'd like to comment on Marie Tharp's legacy, not only in terms of geology and geophysics, but in the area of marine cartography. And this is a vibrant area of research, mainly in the geographical sciences. But at ESRI, the Environmental Systems Research Institute, we are a mapping company, and we are consciously trying to continue the legacy of Marie Tharp. And this is reflected in the ocean base map that we have created. There is a lot of research that's gone into the color saturation, the hues, the label placement, the angle of the labels, the projection, the coordinate systems, as well as the compilation of authoritative data in this base map from GEBCO and the USGS and NOAA and various research institutions such as Huey and Scripps. So we actually have dedicated our work on this base map to Marie Tharp. Now, a base map, as you know, is something upon which you can overlay. So this base map is actually a web service. It's in the cloud. The bathymetry is in the cloud, and you can overlay animations, such as this animation of the marine debris field from the 2011 Tohoku Oki earthquake and tsunami, all manner of points, lines, polygons, rasters, and so forth in the tradition of a geographic information system. We're working also now on polar base maps in the proper projection. There is a seafloor geomorphological base map, again, under the tradition of Tharp, with a very nice legend in terms of what those colors mean on the geomorphology of the seafloor. There is also the legacy of Bill Haxby and the famous Haxby colors from Lamont. And we very much appreciate the work of Suzanne Garbat and Kirsten Leonard and Vicki Farini. We also are thankful to Marie Tharp for helping dispel the notion in this infamous New Yorker cartoon that many of us have seen. And I would encourage you to go to the Heesen and Tharp collection in the Library of Congress here in Washington, D.C., where you can actually see these items. I don't have time to go through this wonderful quote that Marie Tharp uttered in 1999, but if you'd like to have a copy of this presentation, you can go to the web address that you see, and also I would encourage you, if you haven't already, to read Hallie Felt's book, Soundings. It is quite eye-opening and instructive. Thank you so much.
Thank you so much, Don. Why doesn't the next speaker, Claude Jopard, come up now while we're taking questions for Don? Yes, there's a question right there. Repeat the question.
So the question was, who prevented Marie from publishing? And it was really a matter of culture at the time. It may be the secrecy factor that Naomi has identified, but in terms of culture, women just were not co-authors, at least in the Ewing lab, as described in Hallie Felt's book. You know, Marie started off as a drafter, as a research assistant, and she was not recognized as a scientist who actually came up with scientific concepts that were worthy of publication. She was more seen as a research assistant. But Bruce Hazen was a very wonderful advocate for her and for her intellectual prowess, and that's why she was included from 1959 forward.
Marie used to talk about if there was an area that heat. So I take it you guys don't carry on that lovely tradition among cartographers anymore.
That's one of the, that is an absolute essential. You must have a key or a legend.
And hide the material you don't know. That was what you did.
You can lie with maps, but you can also reveal truths as well.
That's great.
Thank you.
It's a great closing line. We're pleased to have Claude Jopard from the IPGP to talk about Harry Hess. I should say that Claude is the Hess medalist, and that's why he has this special honor.
This is the hour. Okay.
So this is the mouse, and this is the
Okay.
echo.
Yes. Hello. Thanks for being here. When Ross asked me to talk about Harris, I was really wondering why, but I think Naomi Oreskes gave me the answer. I was never part of the U.S. Navy. So anyway, everybody knows maybe about this is a famous picture of Harry Hess explaining his seafloor spreading model. What is less well known is, as you can see on this part of the picture, you can see a boat with a drill rig. Harry Hess was involved in, I think, the first deep-sea drilling experiment. It turned out to be a failure for reasons that we won't have time to talk about, but I think it gives us a clue of what Harry Hess was interested in. He was not only interested in seafloor spreading, but he was interested in the rocks that are produced. And I think that I will try to convince you that if you don't understand the rocks, you can't understand the Earth. Just to give you a small historical perspective, starting from the 1800s to the basically seafloor spreading and plate tectonics, you can see that most of the 19th century was devoted in large-scale models of the Earth, starting with circular cooling. It started, I'm sorry to say, by Fourier, who developed his theory of heat conduction precisely to work out how the Earth was cooling down. Why he never pushed this far enough for geologists is an open question, but his first memoirs were about the circular cooling of the Earth. And of course, that led to models of the mountain belts being due to shrinkage due to cooling. And lots of questions were also raised about the rheology of the interior of the Earth, whether the Earth was elastic or whether it was flowing, and also about isostasy. And of course, isostasy can only be sustained if you have sufficient flow in the deep interior of the Earth. And so this was the picture when the 19th century ended. The age of the Earth was always a problem. And of course, you can see that continental drift sort of started when we did not know much about the age of the Earth, and certainly when we did not know much about the oceans. And I think some part of the problems was indeed we did not know enough about the oceans, and that's what Harry Hess was concerned about, was the oceans. Later on, you can see there's quite a big gap, and most of the activity, once we had sufficient data in the oceans, seafloor spreading and plate tectonics could really begin in earnest. To give you, compare with, say, what astrophysics was about, you can see that things were developing quite about the same rate. We did not know the size of our galaxy until the 1920s. The fact that the stars belong to a continuous sequence of luminosity versus temperature was being sorted out just as we were trying to sort out the Earth. And maybe on a smaller scale, you can see galaxy models, the models of how the galaxy evolved, were really developed as we began to understand the Earth itself. So Harry Hess. Well, Harry Hess, just a summary of his most important works, starting from the 1920s. The really first big scientific endeavor that he started on was the Stillwater intrusion. And I will talk a little bit more about this because Harry Hess was first and foremost a petrologist and a mineralogist. And he was very interested in peridotites. And you will see that peridotites have always played a central role in his research. And you can see that he worked on the Stillwater intrusion for about 30 years. He then became interested in the oceans, participated in submarine expeditions to measure the gravity field. And then, of course, he got fascinated by the oceans and by the lack of knowledge we had about the oceans. His History of the Ocean Basins, which was published in 1962, but was slightly earlier, is justly celebrated. But you can see also here that he finished his Stillwater memoir just at the same time. It's as if 1960 was the point in which everything came to fruition. I think one paper which had been overlooked is a paper that was published in the Transactions of the Royal Society of London about the Earth's crust under the oceans, and I will come back to that. And that was earlier, that was 1954. To give you an idea of what for petrologists and mineralogists our current understanding of the Earth was, when he started the work, it was not clear that the Earth's mantle was made of peridotite. In fact, there was a lot of disagreement about this. And it was also not clear at all that basalts were that important. Petrologists were mostly concerned about granites, and it was certainly not known that basalts could be generated by the partial melting of peridotite. I think there's a few landmark things, although Bowen had shown that you could generate basalt by peridotite. It shows a feldspatic peridotite, which is not really the one that exists in the mantle, and that thing was largely forgotten. In 1950, tholeite was recognized as the major basalt for the oceans, and it's not the basalt that you see most frequently in continents, so that was really a warning sign. And then it was only starting in 1954, something like this, that it was realized that the upper mantle was made of peridotite. And it's only in 1962 that the first experiments demonstrated beyond doubt that basalts were generated by the partial melting of peridotite. Decompression melting, which had been mentioned previously, was firmly established as the main mechanism to generate basalts in 1967. You can see that for a petrologist, all this knowledge was still shaky, and Harry Hess had to work in this environment where the rocks were not very well understood. You can see also that he worked on the oceans and the mineralogy. How did he manage? Well, you can see that it was always in his career that he was able to carry out two different strands of research with a lot of dedication and precision. So I've given you a few excerpts of his publication list. The green is the work that he's done as a petrologist and mineralogist. You can see it keeps on, but the same years, he always published things about the larger scale picture of the Earth. And I think that's what distinguishes him from most of the other scientists. He was really a well-rounded scientist, worrying about the rocks, worrying about petrology, but also worrying about the Earth as an evolving system. Quite remarkable to see how consistent he was in his interests. He was interested in the oceans, and he published, I think, the first structural map of the North Pacific ocean floor. That was published in 1942, summarizing all the data that was available then. And he tried to define what he could see, or outline what he could see as definite structural features of the ocean floor. These are the things that he outlined there. It's a wonderful map, if you look at it, given the data that was available. And there are several things that he discussed. One, for example, is the Olivine swell. And he realized that, of course, it was characterized by volcanoes, but by a very broad area of anomalously shallow seafloor, much too big to be accounted for by volcanism only. And I think he was the first one to call that the Olivine swell. He also recognized that there were linear features that would extend across almost all the oceans. And I'm not sure about this because I couldn't trace it back, but he called them fracture zones, and maybe he was the first one to characterize them as such. He had also, of course, it's also well known that most of the seamounts were in fact volcanoes that had subsided. The other things that he noticed, of course, is that the structural trend defined by what he called fracture zones were at angle to the Olivine swell. And he said that that's something which has to be explained. He couldn't at the time, but he really saw that. So I think he should justly be remembered by the first structural geologist of the ocean floor. Now to the Stillwater Complex. Why is it important? Well, Harry Hess was always interested in peridotites. His thesis was on peridotite. You can see you can do field work with a bit of a class in those days. And that's the Stillwater intrusion. That's an enormous intrusion. Some of its rocks are peridotites. It's a basalt that crystallized, and he was, of course, very interested how you can generate peridotite out of basalt. He realized there were other types of peridotites, but that was the main interest for this particular study, and it took 30 years of his life to sort this out. He was a pioneer in this. For those of you who are interested in petrology, the later work by Wager, Brown on the layered intrusion was started later, because he started in 1931, and most of the work on the Skagerrak intrusions and the layered intrusions were slightly later. And he published this memoir in 1960, which for petrologists is a landmark memoir, and it's full of data. And the stress on this I would like to emphasize here that it's a quantitative mineralogical study, because it is quantitative. And this is an enormous intrusion, and Harry not only measured everything on it, but he also measured the crystal size, took the pains to measure density, and figure out how crystal would settle, etc. It's a quantitative study, and that summarizes his approach to this type of problem. So in 1964, to go back on his work on the oceans, I think the main thing, if you read this paper, the main thing that struck him was the discovery that the moho was shallow under the oceans and not much shallower than the moho under the continents. And you can see that in this picture, it's basically right. Basalt, peridotite, and the thicknesses are correct. I would also like you to see that he was working in very weird units, kilograms per centimeter squared. But anyway, he had the numbers right, and that's basically a complete picture. And this is the way he explained the seafloor. He had convection, a rising cell of peridotite, and the basalts were not generated by partial melting. He could not possibly know this, but there were basalts intruded there. And that's the first picture where it clearly he was in favor of convection in the mantle, and he was also in favor of the picture that you see here. He changed his mind in 1962, and that's the picture of the oceanic floor versus the continental floor. You can see now the basalts have disappeared, and I think that's very interesting to know why. He was not happy with basalts simply because he could not see how basaltic flows on the seafloor would somehow manage to keep a constant thickness. And the data at the time showed that indeed the basalt and the oceanic crust was quite constant thickness. So for him, the constant thickness was an indication that the base of the moho was due to a phase change or a reaction front, and he proposed hydration and serpentinization of peridotite. And in his 1962 paper, he had about everything right: convection in the mantle, the fact that the mid-ocean ridges are relieved just due to the fact that it's sitting on its hot mantle, so because its hot density is lower, so it has to be a topographic high, and also the sediments. And it's interesting also how he calculated the age of the seafloor. He used both the paleomagnetic drift rates for continents. He used the thickness of sediments, but he also used the number of volcanoes on the seafloor, and he arrived at an age of about 200 million years. So a very consistent picture. So I think that's what Harry Hess was. He was a petrologist and a geophysicist. And for him, it was important. If you're a petrologist, you're fine with defining a rock. But if you're a geophysicist, you have to explain why the rock is that thick. And vice versa, if you're a geophysicist and you have a rock which is that thick, you have to explain why it is made of that particular rock. And that's what I think made the difference. And I'll leave you with these words of wisdom that he left us, and I'll leave you there. Thank you.
Thank you, Claude. Are there questions? Yes.
Well, to add one other
Hank.
thing about Harry, he was able to look at new sciences and actually think hard about them and change his mind, even though at a later age. He strikes me as unusual in that regard, too.
Yeah, he always acknowledged that he could be wrong, and yes, many of us should heed that advice, I think.
Thank you so much.
Another comment?
Yes, Lynn Sykes.
At this same time, Bob Dietz was doing a lot of similar work on a big scale, particularly with sediments and reinterpreting data for geosynclines. He was, I think, a better publisher than Harry Hess was in the early 1960s for a variety of reasons. But we should think of him, I think, at the same time as Harry Hess.
Thank you, Lynn. And now Gordon West is going to talk to us about J. Tuzo Wilson. This is your mouse.
Okay,
And then if
that's
you
for
want to
pointing, and
advance
this
the
is for
slide,
changing.
the black one.
Thank you very much. Wilson's key contributions to plate tectonics occurred in the time interval of 1960 to 1967. If there are younger people in the audience, that's maybe even before you're born, you may not know very much about him. So I'm going to try to give a little bit of background. First, you'll know him as Tuzo Wilson, because that's how almost all his publications I'll show, and you may wonder about that. That's his mother's maiden name, and his middle name is Tuzo, and he used that simply to keep a separation between him and another J.T. Wilson who was an American seismologist. In his family, he was called John or Jack or Jock. Let's get on. Wilson was born in 1908 and in Ottawa, Canada, of professional parents. He went to school there, and his family was quite outdoors oriented, and he managed to get work as a junior field assistant, basically just a portager and things like that for geologists in the Geological Survey of Canada. So he spent his summers canoeing around lakes and things. This undoubtedly was where his interest in earth science came from. He went to the University of Toronto and entered, because he was a good student, he entered maths and physics, which didn't have any geology orientation in it, but he was spotted by a professor, Lachlan Gilchrist, who was doing some geophysics, and he arranged a special program in physics and geology for him. When he graduated, he did well, and he got a scholarship to Cambridge, which is an important connection in his life, and spent a year there. Had lectures from Harold Jeffreys, and he said later that he realized he wasn't into mathematics. To that. So he did get employment with the Geological Survey of Canada. He came back from Cambridge. He had to go do a PhD. He went to Princeton University. There worked in Professor Field's department, and was sent to do a PhD in Montana under structural geologist Taylor Thom. When he finished that, he got back and he was employed by the Geological Survey of Canada, mapping in various parts of Canada. I want to mention that when wartime came, he went into the Army as a junior officer in the engineers, and at the end of the war, he was chief of the Canadian Army's Operations Research Department. So somebody decided that he was the person with some initiative and ability. When the war finished and everyone was dispersing, there was some geophysics in the physics department at the University of Toronto, but it had pretty well, no, not yet. It's gone back. So we're still over here. And, excuse me. So he was he was called by the chair of physics and asked to rebuild the geophysics in the physics department because it had really dispersed during the war. Everyone had left. So what did he do there? He was very good at finding people, building communication links and so on, and he managed to bring in a whole bunch of young scientists, and he started up work in all kinds of areas that you can... I don't know why the mouse shouldn't be doing that, but anyway. And so there was a very active program there. And he was involved in, he was made the Canadian delegate to the IUGG, and he got involved in IUGG affairs. And this, again, increased his international contacts. Geophysics at U of T was in an old house here, 49 St. George Street. It was rather famous back then. So what was Wilson's own role? He wrote papers on mountain building. This was global geology, and from a structural point of view, was his personal interest. And he wrote papers with Adrian Scheidegger on contraction theory, and tried to fit mountains into that. He did everything he could to travel, Southern Africa, South America, Northern Australia, New Zealand. He certainly had a chance to see world geology. Now, in the late 50s, Wilson started a project with Villa Uniform funding, that's US military, and to compile global geology. And he learned about things that Hess was doing, and some of the things by internal reports. At least we believe so, although there's not much in the way of records for this. He had his own program. Besides the compilation of continental geology, he was very interested in ocean islands and was finding them all to be young. So he had a fixist background, and his mountain building ideas were based on that, but it all began to waver. In 1961, he attended the Pacific Geoscience Conference in Hawaii, where Dietz presented his paper on seafloor spreading. And that was a landmark. I guess Dietz did submit his paper to Nature, and I guess Wilson was a reviewer because he got to write a 3-page commentary on the paper where he basically announced that he accepted what Dietz and Hess were saying, and he was a mobilist, if you like. So, in 1963, he begins his own publication on this area with this paper, Hypothesis of Earth's Behavior, in Nature 1963. He's compiling information that he didn't get by himself. It all comes from other people, but he has the background to be able to link things together. The paper itself doesn't reproduce well for you, but here's the Pacific, and here are the main ridges and so on. This section here is pretty well exactly what you see in a modern textbook. That to me says a great deal. The problem with that paper is that it's an academic paper. Nature is difficult for anyone who's not directly interested in the science to read. And so he also wrote almost the same material in a paper in Scientific American, and it had much better illustrations. So here is it, Wilson's compilation of ridges and trenches and defining plates without using the word plate. And here is Lohmann's 1997 compilation. And you can see, while it certainly lacks some details in the where things get complicated, it's very much the same picture. Did it have a big impact? It certainly excited some people, but average geologists did not really spend a lot of time thinking about global tectonics. And they were rather unconvinced. And there were a lot of reasons that they could put up why this was maybe not right. There were the long fracture zones in the Pacific and the Atlantic that traversed the ridges and trenches, and he didn't have an explanation for those. And the ridges and trenches aren't really that traceable into the continents. Marine magnetics was beginning to show that there was magnetic striping of the ocean floor. People didn't know what to make of that exactly. The history of the Earth's main field, and the existence of polarity reversals was still very controversial. And paleomagnetism and its support for continental drift remained, especially in North America, quite debatable. Oops, I went back. So Wilson went on to try to improve his hypothesis, and he took a sabbatical to in 1964-5 to work at Cambridge, and there he was investigating the different types of deformation that must surround a non-deforming plate. So he prepared the paper in Nature, the transform faults paper that's so famous. I'm not going to try to tell this audience what transform faults are. I think I'll skip that. But, I went back. I'm sorry, I'm not very good at this. Wilson was in Cambridge, but he wasn't at the geophysics department. But it turned out that Hess was there on sabbatical also, and Vine was there, a PhD student who'd working on magnetics of ridges in the Indian Ocean, particularly. And they all got together one afternoon, and Wilson explained his new views about ridges and trenches, and here's this North America. He had the whole world worked out, but he had predicted a ridge here. And apparently Hess said, oh, gee, if there's a ridge there, there's an excellent magnetic survey of that area here. That's it. But Vine had to run upstairs to the library, get it out, bring it down. And so what did they find? Right where the predicted ridge is, here's the central magnetic anomaly, and here it is blown up. Not only that, it's symmetrical on both sides. So, eureka. We've confirmed two things. Wilson's idea of transform faults and where ridges fit into the ridges and trenches fit together, and the magnetic imprinting. So later, when Wilson was trying to convince others of this, he gave a lot of talks, and he used a paper demonstration of how transform faults fit to ridge offsetting. And you can see here, if I don't trigger a slide change, here's a ridge. It's got an offset in it. There's another offset here. And if I start this, thank you. Here we are, and if you focus right on the offsets, you see that's the only place that the two pieces of paper are moving relative to one another. The rest are just fossilized old regions of motion. So this was also a great landmark, and it explained the ridges and trenches, the offsets of ridges. Yeah, I'm doing that now. So Wilson went on to try to convince a lot more Earth scientists of the reality of plate tectonics. He continued to explore the history of drift, and he won a packet of awards, which I won't go into. It's not too important here. But I would say between 1960 and 67, he managed to put in place qualitatively most of the essential elements of the plate tectonic paradigm that we know today. He also defined the term plate tectonics along with transform faults. I don't call that the plate tectonic revolution. What the plate tectonic revolution was when the bulk of the scientific community all got on board, and the aspects of it were amazingly elaborated and beautifully quantified. Magnetic reversal time scale was all worked out, and plate motion was directly measured and displacement history quantified. But I believe this was the, if not the end, it was the end of the beginning of plate tectonics. Thank you.
Thank you. We don't have time for questions on this talk, but we have an afternoon session where there'll be many more opportunities. And so Meredith Nettles has come up, and we will just... Why am I not getting this mouse? Okay, here we go. And so I'm pleased to have Meredith Nettles speak about Lynn Sykes.
Thank you, Ross. Whoops. Great. Okay. Well, thank you. I have the privilege today to discuss some of the contributions of Professor Lynn R. Sykes. And we'll focus on his contributions to the development of the theory of plate tectonics, though, of course, his career has been much broader than that. But what is it that he did that leads us to be talking about him today in a session on the giants of tectonophysics? Well, if we had to choose one contribution, one single paper that is the greatest contribution to the development of plate tectonics, it must be this one. In 1967, Lynn wrote a paper, Mechanism of Earthquakes and Nature of Faulting on the Mid-Oceanic Ridges, in which he presented 17 earthquake focal mechanisms. These results would provide validation of the hypothesis of seafloor spreading. And that's probably enough to make you a giant of tectonophysics right there. But I'd like to provide some of the context for this work. In other words, what was Lynn doing before he published the 1967 paper? He was doing big data and supercomputing. He developed a technique for locating earthquakes using computer algorithms, an IBM 7090, and a lot of punch cards, and he applied the technique systematically to try to understand global seismicity. And I want to emphasize the aspect of understanding the seismicity. These papers, of which a sample is shown on the right-hand side, are not just lists of earthquakes. They incorporate also a wide range of available literature to come up with new interpretations and new understanding of the seismicity. If you know Lynn, you'll realize that his undertaking this exercise is probably what led to him becoming a walking encyclopedia of global seismicity and later tectonics. But I want to draw attention in particular to the paper at the top of the list there, Seismicity of the South Pacific Ocean. This paper was published in 1963. And as we saw earlier, this is a time when our view of the global oceans changed from one in which ocean ridges had become evident to one in which the fracture zones and ridge offsets were emerging. But it remained unclear whether the fracture zones that offset the ridge crests were the result of transcurrent faulting, transform faulting, or perhaps something else. In Lynn's 1963 paper, he located earthquakes from a time period of about 6.5 years, achieving location accuracy about an order of magnitude greater than that previously possible. He found that the earthquakes in this setting were aligned in narrow bands, and importantly, that the activity along the fracture zones was restricted almost entirely to the regions between the offset ridge crests. At the Eltanin fracture zone, indicated by the orange circle there, he found that the seismicity was offset by nearly 1,000 kilometers along the fracture zone. Here's a modern view of the seismicity of the El Tannin, with more data, more computers, and another order of magnitude improvement in the earthquake locations. But the result is the same. The earthquakes are confined to the fracture zones in the regions between the offset ridge crests and don't extend outside of them. From today's perspective, this might be enough to answer the question of transform faulting versus transcurrent faulting, or rather, Lynn's 1963 result might be enough. However, it was his 1967 paper that really laid the issue to rest. As we tell our students in introductory geophysics every year, we expect different earthquake focal mechanisms for earthquakes occurring on transform and transcurrent faults. In the Atlantic, as you see in the cartoon on the left, the ridge segments step to the left as we move north. In this configuration, if the ridge segments are passive markers of fault slip, like segments of a fence being offset across a fault line, as shown on the right-hand side, we expect left lateral motion on those faults and beach balls like the one at the lower right. If instead we're generating new seafloor at the ridge segments, leading to differential relative motion only on the segments of the fracture zone in between the ridge segments, we expect right lateral motion and focal mechanisms that look like that on the left. So Lynn's 17 focal mechanisms would provide the key test of Wilson's transform fault hypothesis, published in 1965. Lynn's work was facilitated tremendously by the availability of data from the Worldwide Standardized Seismograph Network, the WWSSN. The network was global and uniform, it was well calibrated, and critically, this meant the polarities at the stations were well known. So I've been trying to build suspense here, even though you all know the answer. And here it is. As you can see from the plot, there are the ridge segments stepping to the left as we move northward in the Atlantic. And at the locations of the red dots, those 4 earthquakes, the focal mechanisms, as you can see, show right lateral motion on the transform faults. Or maybe you can't see it because you're not used to looking at slightly old-fashioned focal mechanism diagrams, or perhaps because, like me, your eyes are not good enough to distinguish between the polarity symbols for the P waves plotted inside those beach ball diagrams. So here's what they look like. Right lateral motion on the transform faults, as expected for the transform hypothesis. So this is the key piece of evidence that validated the hypothesis not only of the transform faults, but of seafloor spreading. Here's the modern view of that same map region. Instead of Lynn's 4 well-constrained focal mechanisms, we have nearly 1,000 well-constrained focal mechanisms in the same area. I'm not going to try to point. Down towards the lower right, around the equator, you see the Romance fracture zone. Up around 10, you have the 10 degrees north, you have the Vima fracture zone. And across the entire region, all of those fracture zones, those transform faults, show right lateral focal mechanisms. So it still works the same way. Having established and validated the hypothesis of seafloor spreading, Lynn continued his systematic work with global seismicity and was able to tie earthquakes in other settings, notably the subduction zones, into the framework of plate tectonics. Here's a paper in 1966 in which he established that all of the earthquakes under the island arc of Tonga and Fiji, extending from the trench itself down to depths greater than 600 kilometers, all could be contained within one relatively thin sheet of earthquakes, connecting the deepest earthquakes to the surface. He also pointed out that the shape of the earthquakes, even at great depths, mimicked that of the subduction trenches at the surface. In the map on the left for the Tonga-Fiji region, you see plotted the earthquake locations at depths greater than 500 kilometers. And the shape and curvature of those location patterns mimics nearly perfectly the shape of the trench and its curvature at the surface. On the right-hand side is a cross-section taken looking face-on into the subduction zone, approximately south to north, where you see the near continuity of the seismicity from great depth all the way to the surface. Lynn concluded in this paper that the earthquakes at depth all the way up to the surface, the trench, and indeed the volcanoes sitting above the trench must all be linked and created by the same tectonic process. Here's the modern view. More data again, more computers, and the picture looks the same. On the left is that same map region, this time plotted with focal mechanisms, and the same cross-section on the right-hand side. Many, many more earthquakes, but all supporting the same framework. Of course, in the modern view, this is complicated. The focal mechanisms are complicated, and we don't have a good understanding of what allows these earthquakes to occur at such great depth. But the basic framework is only supported by more data. In 1968, Lynn Sykes wrote with his co-authors Brian Isaacs and Jack Oliver a long paper entitled Seismology and the New Global Tectonics. The footnote 2 there, by Lynn's name, indicates that the order of authors was drawn by lot. For those modern types way in the back there, this is like having your author order determined by a random number generator. What they did in this paper was assess the available seismological evidence and concluded that within the entire field of seismology, there appeared to be no serious obstacles to the new tectonics. They also built on Lynn's earlier work with the deep earthquakes, tying deformation in individual earthquake events to the geometry and strength of the subducting slab. Take a look at the figure on the right first in this case, which is the modern view of a cross-section through Tonga. The red symbols are earthquake locations, the black sticks, axes of maximum compression, or p-axes. Now compare it to the diagram on the left, drawn schematically by Sykes and co-authors using far fewer data. In addition to the standard underthrusting events at the plate interface, they documented and recognized tensional events at what we now think of as the outer rise, horizontal tension as the slab is bent sharply down into the mantle, and in Tonga, a dominance of down-dip compression associated with the strength of the lithospheric slab. Other subduction zones we now know show slightly more complicated patterns, but again, the basic framework remains. And Lynn and his coworkers had succeeded in tying earthquakes all the way from the deepest parts of the upper mantle up through the slab and then all the way back to the ridge transform system into the theory of plate tectonics. With the framework of plate tectonics established, Lynn turned his attention to the implications of that theory for seismicity and seismic hazard and a number of other topics. With the constant loading implied by the plate tectonic theory, the concept of the seismic cycle arose, and Lynn contributed to and led helping define and refine the conversation about seismic gaps and earthquake prediction in the subduction setting, but also coming back to the mid-ocean ridge system. In his 1967 paper, he had pointed out that analyses of earthquake periodicities at time and space might provide interesting results if a relatively simple system could be used. Here's a recent paper where he illustrates that seismicity is not uniform across the L-tannin, with some regions of almost no seismicity and others of perhaps repeating earthquake cycles. So Lynn continues to contribute to the understanding and evolution of these issues. Now, this is a tectonics session. I see I'm running out of time, but I would be remiss if I did not mention the other main branch of Lynn's research. He has been a clear and consistent voice for the scientific basis for successful verification of nuclear testing treaties. This paper, published in 1982 in Scientific American, not Science, not Nature, but Scientific American, is the one that Lynn would point to as his second most important contribution of his career. In that paper, he made a clear and compelling case that, and I'll quote, "The technical capabilities needed to police a comprehensive test ban down to explosions of very small size unquestionably exist. The issues to be resolved are political." And that statement is as true today as it was 36 years ago. So if you haven't read this paper, I urge you to do so. I'll also suggest that you have an interest in pursuing either of the topics central to Lynn's career. You might read the books he himself has written in the last couple of years, where you will find a more eloquent explication of the arc of Lynn's career than I have been able to provide. I'll thank Lynn for his continuing contributions to science and education, and I thank you for listening.
Thank you, Meredith. Lynn, do you have any questions about your life? Any other questions? while we change speakers. Okay. Also, I'd like to introduce Margaret Jadamek, my co-convener, who will now introduce the speakers. So we need to get this guy going. So that closed. It goes here, right? Okay. Okay.
Okay, great. I'd like to introduce Hank Frankel, and he'll be speaking about the contributions of Jason Morgan.
Jason Morgan. In my abstract, I mentioned how I think he and Dan McKenzie should receive a Nobel Prize. Remind me if I don't mention that again, I'll conclude at the end and say why I think that's the case. Jason was born in 1935. In 1957, he received his undergraduate degree in physics from Georgia Tech. And then he spent 2 years in the Navy, but as we'll see, they weren't wasted 2 years. Now, he then decided he wanted to go into physics, and he embarked on a PhD program at Princeton, working with Bob Dicke. Now, Dicke at the time was interested in possible fluctuations in gravity, that G was not a universal constant. And what he did was he set the following task for Morgan in his PhD, to look at the geophysical and the astronomical implications of a change in G with the fluctuations. And Jason finished up his PhD in 1964, at the end of 64. And there are several things to remark about what happened to him and what he did. The first is that he decided to go into geophysics, that he was no longer, and the reason was he viewed geophysics to be data-rich, unlike at the time physics. A little softer, okay. So the first move then was, I'm going to end up working in geophysics. And he applied to Princeton for a postdoc, and to mention Harry Hess here, Harry had the wisdom to get people in geophysics in the geology department at Princeton. And he convinced those that needed convincing to do as such, and Walter L. Sasser was hired in 1964. And Jason becomes a postdoc student working under L. Sasser. The other thing that happened to Jason, or two other things that happened. First, he had to read a lot of geophysics, given his thesis. And he read Jeffreys' The Earth. He loved it. And he loved the mathematical treatment that Jeffreys offered for a rigid Earth, given the assumption the Earth is rigid. That was the first thing. The second thing is that he really enjoyed a book tri-authored by Tuzo Wilson, the book on physics and geology with Jacobs and Russell. That also affected him. What he liked about that was that they treated geological problems and issues by using physics. And the third thing that he appreciated enormously, which he didn't mention until 25 years later when we had a session about the 25th anniversary of plate tectonics, is that 1963 paper by Tuzo Wilson published in Scientific American that's already been mentioned. And he was impressed by that, not only because of the discussion of continental drift and seafloor spreading, no transform faults yet, but by the suggestion that there was a thing like a hot spot underneath Hawaii that caused the formation of the Hawaiian Islands. Okay, you can see why in retrospect that was so important for Jason. Okay, so the last thing. Jason defended his thesis in September of 1964, and there was a public presentation and defense of it, his orals. And Harry Hess was on the committee. Hess was on the committee because Jason had worked in geophysical elements, aspects of a change in fluctuation in the gravitational field. So Hess heard him go on about Jeffreys. And the story is that Hess, after the orals, gave him a copy of a paper he wrote that was published in 61, History of Ocean Basins. And he said, Jason, I think you ought to look at this. So it was a good idea. Now, we mentioned petrology and Hess, and this comes in the story in the following way. Guess who arrived in Princeton? The person who arrived in Princeton was Fred Vine. And Fred Vine and Jason Morgan shared an office beginning in 1965. And as Jason put it, you know, I understood the seafloor spreading part of seafloor spreading without a problem. That was easy. But the petrology, and thank golly that Vine was there to explain it to him, because that's basically what happened. Because Vine, as you know, is a petrologist too, besides Hess. Okay, now he begins working with Elsasser in his postdoc. And Elsasser pretty much leaves him alone. He's interested, Jason is interested in the origin of trenches. And he had planned to read a paper at the 1967 spring meeting of AGU here in Washington on trenches. But what happened? What happened is in January of '67, Bill Menard published a paper where he talked about the great fracture zones of the Pacific. And here is the figure now, the figure's up there, showing Menard's figure. And Menard said, you know, what's really interesting is that these great fracture zones almost are great circles. Now, Morgan looked at it. How do I advance?
So you can advance just by pushing this button.
So what Morgan did was, Morgan looked at that figure, and given his training in the Navy during those 2 years, there was one afternoon they spent on various map projections. And Jason recognized that, wait a minute, it's not that they're almost great circles that's important. What's important is that they are almost concentric small circles. And given that he was a physics undergraduate major, and he knew about Euler's point theorem as an undergraduate, he immediately thought, well, look, if these great fracture zones are fossilized transform faults, then I've got Euler's point theorem, because I've got the concentric circles. So that is the birth in his mind of what we call plate tectonics. Now, the key deal here was that it only works if the outer surface of the Earth is to some depth or whatever is in fact rigid. So what he does is, in his testing of plate tectonics to find out if he can get Euler poles, he's also testing at the same time the rigidity of the outer surface of the Earth, the blocks that might move relative to one another. And so what he does is he devises two tests to find out if, in fact, and this is a famous figure that many of you have seen before, to find out if, in fact, if these 20 or so blocks, as he called them, in fact move relative to one another in a way they could be described by Euler's point theorem. Now, the one thing I want you to notice in particular with this diagram is, if you look over where the Juan de Fuca is, and you can see the little Juan de Fuca plate there, okay? This was hypothesized both by Jason and also by Dan McKenzie, okay? Because they realized there was a different situation there given the magnetic data off the Juan de Fuca, which was then known, that it was a separate little block. And I think that's actually significant. Okay, how does he test it? Now, we've heard about Marie at this point. Well, here, in fact, are the not transform faults. They didn't call them that. As you know, that was Tuzo's contribution here, a gigantic contribution, and also by a man named Coode, too, who came up with the same idea. What he does is, Morgan takes this particular figure, and he realizes, look, I'm going to draw perpendiculars to it, okay, and find out if they indeed intersect. Now, he treated North and South America as on the same plate, okay? But in this case, he realized that he was really just testing Africa versus South America, given the placement of these fracture zones, or we'll call them transform faults. Well, here are his results. And it's nice that Lynn's in the audience here, too. I think he may appreciate this, see if we get this right. This is the diagram, your 8A diagram here with all the lines in it, is dropping perpendiculars to the fracture zones, okay? And you get a nice, good intersection there of the Euler pole. But as Jason pointed out, although I've got a really good tie here on the longitude, it's not so good on the latitude because of the grazing of the intersecting lines. Now, as a little side issue, he also said I should look at first motion studies. So he looked at some of Lynn's work here. This is earlier than the great papers that came afterwards, okay? And those, you can see the results on 8B. They're not all that good. And Jason sort of suggested this could be an issue of accuracy of the work, or in fact, they may not be straightforward strike-slip faults. They might have another little ingredient in them. So he dismissed these results. Now he moves on to the second test, the seafloor spreading test, okay? There are the magnetic anomaly test. He knows immediately that the rate in seafloor spreading will just simply follow a sine curve, okay, with a maximum at the Eulerian equator. And here's you can see the results here are very nice to the theoretical prediction, okay? And this also allows him to pinpoint the latitude, okay, of the Eulerian pole. And he takes this definitely to be representing Africa versus the relative movement of both Americas relative to the African bloc, okay? So in this case, he's been able to get consilience to a fair degree by using both the magnetic anomaly, the seafloor spreading technique, and also the transform fault technique. Now he moves to the relative motion of the Pacific to North America and South America, okay? And in this case, because of the wide separation in latitude here of the transform faults, about 50 degrees here, he's able to pinpoint both the latitude and longitude of the Eulerian pole with respect to the Americas and the Pacific. Okay, and you can see the results here are pretty, why do I keep pointing at this? The results here are pretty good, all right? And in the second one, the lower figure here, what he's done is use first motion studies. And except for that outlier, these turned out to be pretty good too. So he's got, in a sense, a corroboration by these two techniques, and now he moves to the relative motion of the Antarctic block to the Pacific block. Again, he starts out by using the fracture zones. And with the fracture zones, he gets a rather nice pole at 71 south, 118 degrees east. Okay, these are dropping the perpendiculars. Now we move to spreading rates. Okay, and here most of the work was from Lamont. Okay, you see the predicted value there, and this is awfully darn good, okay? So he's got a wonderful corroboration here by both sets of data, okay, independent data sources, to give him the Euler pole. Now, sometimes I think this is not appreciated that much. Both Dan McKenzie, in his version of plate tectonics, and Jason Morgan, in his version, say that they have a kinematic theory, they do not have a dynamic theory. Both of them severed any deep structure of ridges. Okay? Now, McKenzie did it explicitly because McKenzie couldn't figure out why Africa and Antarctica would be surrounded by ridges if you had the active convection currents upwelling from ridges, okay? So what Dan did was he severs the connection just as Jason did. And this removed the difficulty in the acceptance of plate tectonics because it was never faced with a mechanism solution that really didn't work. Now, both of them believed that convection was involved. I should add that. They both believed that convection was involved. And what they both believed was that the actual lithosphere, or the moving part, was part of the convection. It wasn't that there was a Hessian viscous mantle where you had a mantle drag that moved them, okay? That was completely left alone, and work on that obviously has continued on. Okay, now, what I want to do is I want to mention the Nobel Prize issue. And I first want to say is that if you believe they should receive a Nobel Prize, and you want to nominate them, you have to be basically in a physics department or a school of physics, okay? So if you are in one of those, okay, and you think they deserve it, find out if you can nominate them. I mean, if you're a geologist, forget it, okay? You can't. Now, why should they receive such a prize? Well, okay, plate tectonics culminated this revolution in the earth sciences. It finished off the controversy over continental drift and fixism. Next, it gave us a framework, a complete framework here that we still use to solve problems. And finally, it turned earth science into a physics, okay? Because it was plate tectonics where physics actually became explanatory, not just a way to measure things. Thank you.
Thank you. As much as we'd like to, we'll take your questions in the second session this afternoon. Thank you. Okay, so that, she's on a Mac. Okay, so right up here. Why are we having trouble with that mouse? Can you see it?
No, I don't. Is it upside down?
No, it's not. There we go, there we go. You have a magic touch. Okay. Thank you.
And this follows very naturally. Louise Kellogg will be speaking about Don Turcotte and his contributions to geodynamics and plate tectonics.
Okay, thanks. Thank you, Margaret. I really appreciate it. So it is really a delight to be able to talk about the work of Don Turcotte and his contributions as one of the giants of tectonophysics. So let's just get right to it. I'm going to start in 1965. In October of 1965, but leading up to this, Don got his PhD from Caltech in 1958 in aerospace engineering, and and then spent a year at the Naval Postgraduate School in Monterey before arriving at Cornell University as a professor of aerospace engineering, where he was working on topics related to combustion and statistical thermodynamics and various things that were not in any way, shape, or form geological. And in 1965, he's an associate professor of aerospace engineering at Cornell. He's got a young family. He's an avid and champion amateur golfer. And he heads off to Oxford University to the Department of Engineering Science on his first sabbatical leave. There he meets a young Ron Oxborough who had recently received his PhD at Princeton University working with Harry Hess. So we're going to see some connecting threads with the previous talks. And Ron Oxborough had just been elected as a lecturer in geology. Ron was eager to talk to people about some of the theoretical underpinnings for many of the ideas that we've been talking about here. And Don had a very open interest in new and interesting problems, and so they became collaborators very quickly. And together they developed a boundary model for thermal convection and applied it to mantle convection, which helps address some of these underlying mechanisms for many of the kinematic work that we've been hearing about so far. This is their first publication together in 1967, or one of their most important ones, in the Journal of Fluid Mechanics, Finite Amplitude Convection Cells and Continental Drift. And you can see this figure, sort of classic figure, in which they outline the boundary, the presence of boundary layers, basically the presence of a cold thermal boundary layer at the surface that is with a rising limb of the convection cell and a sinking limb of the convection cell. The heat flow here, where the two diverging boundary layers are pulling apart. These are basically the mid-ocean ridge, and it's cooling, and as the boundary layer progresses away from that upwelling until it becomes colder and denser and starts to sink, eventually it becomes unstable and founders and sinks into the interior. And so this basically provides a prediction for a lot of the observations that were critical to our understanding of this. It provides basically a mechanism for the lithosphere to be part of, really a foundational, central part of the convection, the underlying convection. As we just heard, that was an important idea to contributing to this. In addition, it predicts that the heat flow will be high near the mid-ocean ridge and will decline. It predicts the change in bathymetry with age of the lithosphere as the lithosphere cools and becomes more dense and starts to sink. And so this was really a foundational piece of work. The two of these, the two scientists, Ron Oxborough and Don Turcotte, had something like 30 or 28 papers together, a really remarkable series of papers in which they continued to outline the theoretical underpinnings for a lot of plate tectonics and mantle convection. And this really spawned an entire branch of research in mantle convection, and I've just collected here a small, very, very small collection of pictures from different venues. Some of them are textbooks, some of them are kind of public websites or magazine articles about convection. Some of them are numerical models of mantle convection in which basically you can see the influence of this foundational theory of finite amplitude convection in the earth sciences. It also influences the interpretation of seismic tomography. So here's a seismic tomography model in which you can see basically the subducting slab and how it behaves as the downwelling limb of the convection cell. So that's basically the beginning, but this was really only the beginning. So Don Turcotte came back from Oxford. He left as an engineer and came back from Oxford to Cornell as a geoscientist and has remained a geoscientist. In the subsequent years, the Geological Sciences Department at Cornell moved from the College of Arts and Sciences to the College of Engineering, and he joined that department. They hired many of the really outstanding researchers in the area in the then brand new area of tectonics, and really built a very exciting department program that did a lot of groundbreaking work. But this work with Ron Oxborough also led to a series of groundbreaking work in geodynamics. Is very broad. And I'm just going to go through a few of the early papers with a number of students and colleagues that Don published. And I think in the kind of spirit of AGU's centennial, which is coming up next year, it's important to note that almost everything I'm going to show was published in AGU's Journal of Geophysical Research. So that was an important article, or important journal, and still remains one. So we have work such as the look at the structure of the Olivine Spinel phase transition in the descending lithosphere and how its location is affected by the thermal structure in the descending lithosphere. So this combines an understanding of the phase transition and an understanding of the thermal structure and the dynamics. This was by Turcotte and Schubert in 1971. We have a look at, with Bill Haxby, who's also been cited earlier in this session, at the isostatic geo-anomalies and their origin, which combines development of the theory with a development with comparisons with data. This is a kind of underlying theme of Don Turcotte's work, that the theory and data must go together. Data analysis and understanding of the data must go with the theoretical underpinnings. We have some of the first numerical experiments on mantle dynamics. Mark Parmentier, Don Turcotte, and Ken Torrance, who is an expert in numerical methods at Cornell in the Engineering College. These are the numerical experiments on the structure of mantle plumes, and they basically outline the upwelling thermal structure and the origins of melting and how that melt emerges through the lithosphere in 1975, so a very early model of that sort of thing. And then if we move forward, we start to see the influence of many multidisciplinary and interdisciplinary collaborations. And this is also a theme. So starting with the collaboration with Ron Oxborough, there's a theme in which Don Turcotte collaborates with people who bring a different perspective to the work. So this particular collaboration was with Claude Allègre, a very famous geochemist in Paris, and they worked together. They spent several years working together in a collaboration in which Claude taught Don geochemistry and Don taught Claude golf. So the golf, there's a reason the golf ball decorates this. And they came up with the idea, the concept of two components of the mantle being integrated into a marble cake, and it has this sort of famous picture that appeared in Nature. There's a Nature cover to accompany this. The Nature cover was marked up and was sent to the authors, and this is going to be the cover of Nature, but at the last minute Nature decided to substitute something else. So this is the Nature cover that never was, never happened, but it still exists in theory. Okay, so Don Turcotte consolidated a lot of this work into a volume of, many of you probably own this book in one edition or another, Geodynamics. And I like the subtitle of the first edition, which is The Applications of Continuum Mechanics to Geologic Problems, because I think it really covers the entire range of geodynamic theory. And so this is written with Jerry Schubert. The first edition, second edition, and third edition are shown here. One of the things about this book that I think is really unique and important is that this is a textbook, and it has many problems worked out in detail, or assignments so that the reader can work these problems out in detail, these fundamental geodynamic problems. But it has been cited many, many times in research papers. So by providing this theory in an accessible way, it basically allowed many people to do geodynamics-based research or use geodynamics in interpreting their observations and their data. And it has more than 7,000 citations in research papers, which is very unusual for a textbook. There are a couple of others that are like that, but very unusual for a textbook. One of the characteristics of Don Turcotte's research career is that he always is open to new ideas and new approaches. And so in the early 90s, he started to turn his attention to the other planets and posed this hypothesis for Venusian tectonics, which involved the episodic overturn of the Venusian lithosphere, in which the surface is resurfaced very rapidly at episodes alternating with what we would now call stagnant lid convection, in which basically the lid is stagnant and the interior is heating up. I did mention the Gulf, and so I have to actually say something about the Gulf. So the little clipping at the upper left is basically a news clipping from a newspaper in Scotland. St. Andrews, Professor Don L. Turcotte of Oxford, who was on leave from Cornell University, holes out in one on the short 8th at the old course. Not all the Gulf went well. As you can see, he's in the heather on the picture on the right. And this basically was this sort of combination of conversation in the course of doing something else was really inspiring to a lot of the students at Cornell in the 80s and early 90s, and to the extent that a group of students organized an annual tournament. Didn't have to know how to play, but you had to be able to just show up and participate, and so that's a picture with a lot of extremely young people, some of whom may be in the room and may recognize themselves in that picture. I'm not in there, it was before I even got there. Okay, so I'm going to wrap up with just a few seconds of again, the additional work that's been done. In the mid-1980s, Don was told by a student named Bob Smalley, a physics student by Bob Smalley, that he needed to get with modern science and start to think about fractals and chaos as an understanding. And this led to a series of papers and a new approach that he's been working with in the subsequent years, including a book on fractals and chaos in geology and geophysics, starting with a work on fragmentation, which has a very important implications for industry, as well as for just general geological approaches. A series of papers especially with Bruce Malamud and with John Rundle and with others, investigating natural hazards from the point of view of a statistical approach. And so this includes approaches like forest fires and landslides and earthquakes and tornadoes. Many of these are very influential and have really helped to provide a quantitative basis for the understanding of these hazards by looking at all the data available for these events. And most recently, one of the things I wanted to end with is a paper on the science of fracking. And this is a paper that really looks at this very kind of politically charged issue of fracking and the origins of earthquakes. But the authors on this really took the point of view that they should follow the science wherever it takes them. And so they wrote this very recent article in annual reviews to address that, and I think it will be influential going into the future. And so I'll just close with this nice picture, and on behalf of basically all of Don's students and colleagues and so on, sort of thank him for the collaborations over many, many years and the mentoring over many years. All right.
One question. Okay. We have time for, say, one quick question as the next speaker comes up.
I can't see through that light.
Yeah. So you left us hanging. What is the scientific conclusion about fracking?
So essentially, there is an association of fracking with these earthquakes that occur, and but it can be mapped out in terms of the style of fracturing and connected with fundamental physics of fracture mechanics in with liquids, and basically that can lead to some mechanisms for controlling the rate and type of fracking technology used to mitigate those earthquakes.
I just don't understand this. You have so much, okay, connection lost, connection found. It's just having, I guess it's a battery issue. We don't have anything else. Yeah, I think it's a battery. What other, can we just put this guy in there? Can we do that to the Mac? Does this guy have a connect? Where is it?
Our mouse one seems to,
wait a
we
minute.
seem to, we got it
Yeah,
back.
now.
Is there, does anyone know the hotkeys, or maybe can someone step out, see if there's a technician? We seem to have lost oh, here we got it back. We'll try to get it while we have it. The battery's probably up right there.
It's just the moving at the end.
The 4.
It's just the moving at the end.
It
Oh, that-
seems to be working again. Is it died?
Okay. Does anyone know the hotkey to start a PowerPoint?
Okay, so why can't we connect this to?
Okay, well, oh, we got it. Oh, quick, make it. Oh. Okay, well.
Apple A.
What's that, Apple A? Thank you. Open Apple A?
Return.
Oh, brother, let me escape. Open Apple A, return. Did someone just Google that, or did you know? Awesome, okay. Now we have the keyboard arrow keys, so you're good for that. Thank you, I appreciate that. Sorry for the delay. Okay, I'd like to introduce Barry Parsons, and he'll be speaking about the contributions of Dan McKenzie.
Good afternoon. When Ross asked me to talk in this session, I thought about what I might talk about and very quickly decided I wouldn't talk about plate tectonics, as you might have expected. I mean, sorry, let's go on. Whoops.
On the white.
Oh, sorry, yeah, okay. Partly this is because the plate tectonic story has been told many times, particularly in the last year and a bit, where there have been many meetings around the world celebrating 50 years of plate tectonics. And many of the original participants have told their own stories, and I didn't want to repeat that. The other thing is that in 1967, Dan was 25 years old, barely a year out of his PhD, and the plate tectonics paper with Bob Parker was only his 4th published paper. I think he can be excused for not having realized at the time the impact it was going to have, how long it would take to work out the consequences. So he was already thinking, what do I do next? Now, I think 50 years on, we know that he's made a number of substantial contributions independent of plate tectonics, and I thought that their story was well worth telling. The question is, with 50 years of material, what do you choose? How do you pick? And I was struck by this quote, which is at the beginning of an article Dan wrote in Annual Reviews this year. And if you want to know what he thinks about his career, you can read that article. But it was make the point that from the Second World War onwards until plate tectonics, the emphasis of physics in the earth sciences was on making physical measurements, and obviously that was a good thing. But after plate tectonics, the emphasis shifted. Not that the physical measurements went away, but the emphasis shifted to using physics in the modeling of geological processes. So what I decided to do was pick a couple of those geological processes, sedimentary basins, the origin of sedimentary basins, and the migration and extraction of melt from the mantle. Now, other people might choose different things, but what I think is unarguable, these are two fundamental geological processes to the understanding of which Dan has made a lot of great contributions. Now, in the immediate aftermath of plate tectonics, there were two issues outstanding, well, probably more, but the two that I think I'm aware of. This shows the seismicity in the oceans. There's a mask on this, so that the seismicity on in the continents is masked out, and you can clearly see the narrow bands of seismicity marking the deformation between plates and hence defining the plate boundaries. If I invert the mask, so this is now masking out the oceans and you just see the seismicity in the continents, there's no clear picture at all. So the question was, what happens in the continents? Is it plate tectonics writ small, or is it something else? The other problem was, of course, plate tectonics was successful because all it required is that the plates move, and you didn't have to know why or how. But of course, any self-respecting physicist wants to know that answer. And there were two approaches. One is that the plates are rigid bodies, so you treat it like any other rigid body and look at the forces on its edges and boundaries. And this approach was quite fruitful, particularly in the work by Don Forsyth and Seya Ueda. The difficulty is if you want to introduce the velocities, you have to introduce an interaction with the mantle, and this was generally done in an ad hoc way. The other way is to treat it as a whole, a convective system as a whole. Clearly, a large amount of the heat from the Earth is being lost that way. The difficulty there is that at that time, you couldn't include the plates, but that I don't think bothered Dan, because as a physicist, he wanted to start with the fundamentals and build from there. So those are the two problems that he picked up on. Sorry, and yes, all right. Now, I needed a thread to tie the two parts of the talk together. And also, I was reminded by colleagues and friends of Dan that I shouldn't be too reverential. So I thought I would tell an anecdote here. And like the best anecdotes I know, this came from James Jackson in Cambridge. And Dan accompanied James and a Mongolian graduate student of James's on a field trip in the Mongolian Gobar Altai. The fourth member of the party was a driver. And at the end of the first day, they have to set up camp and get food, and the driver takes command and he allocates the tasks. And the graduate student says, well, I'll prepare the food for cooking and things like that. James says, well, I'll pitch the tents. And the driver looks at Dan and says, what do you do? And quick as a flash, the graduate student says, he solves differential equations. Well, the driver pauses and thinks about it, and then he hands Dan a sack and says, you can collect the dung for the fire. And there he is cooking away. Now, the thing that struck me about this story, and I've heard it a number of times from Dan, is the notion that Dan solves differential equations. Of course, there's a great deal of truth in that. He does solve partial differential equations of all sorts, but he does rather more than that. So I took this as my entree into the two topics that I'd chosen. So now I'm going to talk about sedimentary basins, and this is our first differential equation, which is the heat diffusion equation. And this paper it was Dan's third paper, published 2 weeks before the plate tectonics paper, in which he looked at heat flow anomalies at mid-ocean ridges. And it's now called the thermal plate model, in which basically material is advected at the mid-ocean ridges, cools, attaches itself to the plate, and as it moves to the side, loses heat by conduction. Now, this problem has been around for 150 years since the work of Joseph Fourier in the first part of the 19th century, and the solutions are well known. They can be expressed as Fourier sine series. The name Fourier comes from that. And basically, each of the terms in that solution has an exponential time decay on it. Now, Dan was interested in the heat flow at mid-ocean ridges, but this very quickly became applied to looking at the substance of mid-ocean ridges. And if you calculate the substance from this solution, In fact, away from the mid-ocean ridges, just the first of these exponentials, the slowest one decaying, it basically describes everything. Now, people who were working on sedimentary basins picked up on this idea and thought this might explain how you create the subsidence, thermal subsidence might explain how you create the hole in the ground that you need to put the sediments in. And I think the best example, the best I know of this is from Norm Sleep's work in 1971. And he looked at a series of wells on the US East Coast coastal plain. I think their wells were drilled for water. And for various reasons, what he did is he normalized the depths to each of the sedimentary horizons to a particular horizon, averaged them and plotted them, and you see this curve here. And the dashed line is basically what you would expect if you had simple exponential decay of the elevation, excess elevation, with a time constant of about 50 million years, which was what people thought was appropriate for the mid-ocean ridges. And this was great. It meant clearly, thermal subsidence did have something to do with sedimentary basins. The problem was that this area, if you take a material that's originally at sea level, you heat it up, it goes up in the air, you let it cool, and it comes back down to sea level. You haven't actually created any space. And Norm tried to get around this by thinking about erosion, but nothing really worked. And in fact, Dan was the one who came up with the solution, and I think it's arguable that he came up with the solution because he wasn't trying to. What he was trying to do, and he decided to do this when he was at Le Mans at the end of 1967, and as we've learned earlier, this was obviously a good place to learn how to do focal mechanisms and look at active tectonics. In 1977, he was writing up the first major paper of this, looking at the focal mechanisms for the tectonics of an area which stretched all the way from the Azores to Turkey. And this one area, which is the Aegean and the countries either side of it, Greece and Western Turkey, these are the focal mechanism for it. And what they show, obviously, is largely normal faulting with some strike-slip faulting. This is an area of extension, crustal stretching, and obviously, consequently, crustal thinning. Now, what led Dan to the idea for the sedimentary basin thing was the simple physical thing that if I'm stretching the crust, I must be stretching the lithosphere too. And then there are consequences of that. As you stretch the lithosphere, you thin it, if you like, and the mantle upwells underneath. Now he did it at a constant temperature. Now we would say it wells up isentropically. And there you have your heating. That's your heating event compared with what there was before. And as you cool, you will create more space. But the neat thing of this is you're thinning the crust, which creates subsidence. You have a heating event, which creates elevation. But if the crustal thickness is greater than about 16, 17 kilometers, the subsidence wins out. So you have some subsidence at the beginning, and then the thermal cooling will go on. And so you create the space. The figures there are basically shown if water fills the basin in, but if you add sediments, you get an amplification factor, which can explain the great thicknesses of sediments you see, for instance, at US coastal margin. Now, it didn't take very long, about 5 years before this idea was completely accepted and tested by comparing stretching factors from crustal thickness measurements and from subsidence of well data. There's perhaps one area of resistance, which was in the oil companies, not with the younger people, but with older geologists there who were very traditional and perhaps even hadn't taken on board plate tectonics at that time. But geologists and oil companies are entirely pragmatic. If you can show an area, some idea works in discovering oil and gas, they will take it on board. And so Dan combined with an organic geochemist, Andrew Mackenzie, and basically looked at the reactions that occurred in some organic chemicals. And I won't go into the details because I don't know them. But basically, as well as the substance, you can create the thermal conditions in the sedimentary basin. You have a thermal history for each sedimentary parcel. The reactions there are thermally dependent. They have an activation energy. So what you can do is you can follow a parcel of sediment as it subsides in the sedimentary basin, is compacted, heated up, and you can work out where you are with the reactions. And the summary curve for the Pannonian Basin on the right-hand side shows a curve for the two reactions that I've showed, and it has a characteristic path, which was perfectly well satisfied. Now, this paper was in 1983. That year, Andrew Mackenzie went to work for BP, and he rose to quite senior positions in BP, and he took these ideas with him. The chief technical officer of, I am well behind. The chief technical officer of sorry, the CEO of BP once told Dan that he'd sold like a 10-figure sum of money for BP. Now, that's probably an exaggeration, but nonetheless, it shows that they took him very seriously. How much time do I have left, by the way? About a minute. Oh, that's going to be impossible. Okay. Right, but it's okay. It's okay, because I can improvise. Right, so now for the second problem, which is mantle, whoops, sorry, wrong, which is mantle melting. And these are the differential equations here. Don't panic. Clearly, there's a much larger degree of complexity in these equations than the thermal diffusion equation. The interesting thing about this paper, although it deals with solutions and consequences of the equations, I think most people regard this paper, its main contribution is the derivation of these equations, right? So it's not like the other one, which had been known about for 150 years. This was a new set of equations. And I will skip on. What shall I do? Okay, let me skip through some of this. In parallel with working on these equations, what Dan did is he also looked at the geochemical data, and he used rare earth elements to invert for the melt distributions beneath mid-ocean ridges. And you can add up the melt that's been produced, and you can compare it with seismic measurements of crustal thickness, and they agree. And what you find is that the crustal thicknesses are 7 to 8 kilometers, plus or minus 1 kilometer. Now, this plus or minus 1 kilometer is very important because what it tells us is that the temperature in the mantle beneath mid-ocean ridges is very, very tightly constrained. If you increase it by 200 degrees, you get 20 kilometers of extra melt, for instance, for Iceland. So what this means is that the mantle must be very well stirred by mantle convection. Now, this is a figure that I think was shown earlier, and it came out of basically seafloor spreading. And the notion was that you had a hot upwelling, a convective upwelling underneath mid-ocean ridges. And what basically Dan's contribution has been is to show that, in fact, the mantle is very well stirred. When you pull apart the plates at mid-ocean ridges, material wells up isentropically. You don't need any excess temperature there. And I think, as I've run out of time, I will stop and leave out the convection bit and leave it with there. And there may be general conclusion to be made about how science is done, but I'll leave that to the professionals like Hank and Naomi. Thank you.
Thank you, Barry. Well, while we're out of time for questions, we're not out of giants. So this afternoon, we have another session beginning at 4 p.m. where we're going to continue this great experience. Thanks again, Barry.